Recently, astronomers have been confronting a profound puzzle. The James Webb Space Telescope, humanity's most advanced eye on the cosmos, has revealed structures in the early universe that challenge everything we thought we knew. Even Nobel laureates are weighing in, suggesting that our understanding of the cosmos might be fundamentally flawed. The idea that the universe began 13.8 billion years ago, a cornerstone of modern cosmology, may not tell the whole story. Imagine looking at a region of space so distant that the light reaching us left shortly after the Big Bang. In that light, we see galaxies forming, stars igniting, and structures emerging, but they appear far more massive, organized, and luminous than our theories predict. As Dr. Adam Rees, a recent Nobel Prize recipient, remarked, "We may have gotten the universe completely wrong." And he is not alone. The deeper JWST looks, the stranger the universe becomes. When the first deep field images from JWST were released, astronomers noticed something remarkable. Among the countless faint dots of light, some objects glowed far brighter than expected. These were not ordinary early galaxies. One such object, informally called blotch, stands out vividly in the images. It was first observed nearly 2 years ago, and its luminosity immediately puzzled scientists. "We initially thought it couldn't be that distant," said the observing team. "It was simply too bright for the early universe." Subsequent observations, including spectroscopy and cross-validation with other instruments, confirmed its extreme luminosity. This was not a fluke. Something very unusual was happening at the dawn of the cosmos. Blotch is only the beginning. JWST's deep field surveys have revealed thousands of objects in the early universe that defy classification. Many of them do not resemble conventional galaxies. They appear compact, extremely luminous, and, in some cases, surprisingly massive. Traditionally, the lambda CDM model, the standard cosmological model, predicts that early galaxies should be small, irregular, and slowly forming stars. Yet, JWST shows otherwise. Some of these objects contain far more stars than there would have been matter available in the entire universe at that epoch. Dr. Wei Jingyan, an astronomer and co-author of a recent study, stated, "Even if only a fraction of these candidates are real, it would force us to rethink how galaxies formed in the first few 100 million years." JWST allows astronomers to peer past the cosmic dark ages, the period after the Big Bang when the universe was filled with neutral hydrogen, but before stars and galaxies formed. This is the first time we have directly observed light from that epoch. In the deepest field exposures, taken over 120 hours, JWST revealed multiple galaxies forming when the universe was only 200 to 400 million years old. By comparison, the Milky Way as we know it would take billions of years to assemble its current mass and structure. One striking example is the galaxy JSGSZ 14, detected at a redshift of Z equals 14.44. This places its light at approximately 290 million years post-Big Bang. According to standard theory, galaxies at this time should be small and irregular. Yet JSGSZ 14 shows a surprisingly mature structure, hinting at rapid star formation and unexpected organization. The period known as the cosmic dawn refers to the time when the very first stars in the universe ignited. These primordial stars, sometimes called population 3 stars, were vastly different from the stars we see today. They were formed almost entirely from hydrogen and helium, the two simplest elements created in the Big Bang. Without heavier elements, these stars could grow to enormous sizes, hundreds of times more massive than the Sun. When they lived, they burned extremely hot and bright, flooding the early cosmos with ultraviolet radiation. But their lives were short, often just a few million years, before they exploded as powerful supernovae. These explosions seeded the universe with the first heavy elements, carbon, oxygen, iron, making later generations of stars and planets possible. The ultraviolet light from the first stars began to ionize the surrounding hydrogen gas. This process, called reionization, transformed the universe from a dark, neutral fog into a transparent and structured cosmos. Reionization was not instantaneous, it happened gradually, patch by patch, as more stars and galaxies lit up. By about 1 billion years after the Big Bang, the majority of the universe had become ionized. This era marked the end of the cosmic, dark ages, and the beginning of a universe filled with light. As gravity pulled matter together, galaxies began to form. These early galaxies were much smaller than the giant spirals and ellipticals we see today. Many were irregular and chaotic, shaped by frequent collisions and mergers. Over billions of years, these smaller galaxies merged and evolved into the vast structures we know, the Milky Way, Andromeda, and countless others. Strangely enough, black holes also played a crucial role in shaping the universe. Even in the earliest galaxies, supermassive black holes seem to have formed at their centers. These black holes consumed gas and dust, releasing immense energy in the form of quasars, brilliant beacons visible across the cosmos. Quasars were so bright that they could outshine entire galaxies, helping astronomers probe the early universe. The feedback from these black holes also regulated star formation, influencing how galaxies evolved. On the largest scales, matter in the universe is not randomly scattered. Instead, it is arranged in a vast, cosmic web, with filaments of galaxies stretching across hundreds of millions of light-years. These filaments are separated by enormous voids, regions of space almost empty of galaxies. The cosmic web is the largest structure in the universe, shaped by the invisible force of dark matter. Galaxies, stars, and eventually planets formed along these filaments, like dew collecting on a spider's web. The discovery that the universe is expanding was one of the most transformative moments in modern science. In the 1920s, Edwin Hubble observed that galaxies are moving away from us, with their light shifted toward the red end of the spectrum. This phenomenon, known as redshift, provided direct evidence that space itself is stretching. The implication was profound: the universe is not static, as once believed, but dynamic and evolving. It means that at some point in the distant past, everything was compressed into a much smaller, hotter, and denser state. This realization laid the foundation for the Big Bang Theory. The Big Bang Theory proposes that the universe began roughly 13.8 billion years ago from an incredibly hot and dense state. Instead of an explosion in space, it was the rapid expansion of space itself. In the first fractions of a second, the universe expanded faster than the speed of light in what scientists call inflation. As the universe cooled, particles formed, then atoms, and eventually stars and galaxies. The theory elegantly explains the abundance of light elements like hydrogen and helium, the cosmic microwave background radiation, and the large-scale structure of the universe. It remains the leading cosmological model to this day. The cosmic microwave background, CMB, is the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. For the first time, light could travel freely through space, leaving behind a faint glow that still fills the cosmos today. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB provided compelling evidence for the Big Bang Theory. Tiny fluctuations in the CMB map reveal the seeds of galaxies and clusters we observe today. It is one of the most important observations in the history of cosmology. Following the release of the CMB, matter began to clump together under gravity. Small irregularities grew over time, eventually collapsing into the first stars and galaxies. Galaxies are the building blocks of the universe, vast islands of stars, gas, and dark matter bound together by gravity. Over billions of years, galaxies merged, interacted, and evolved into the diverse shapes we see today: spirals, ellipticals, and irregulars. Understanding galaxy formation helps us trace the universe's history from simplicity to complexity. Stars are the engines of the cosmos. They form from collapsing clouds of gas and dust, igniting nuclear fusion in their cores. Fusion converts hydrogen into helium, releasing vast amounts of energy that make stars shine. Stars come in many sizes, from tiny red dwarfs that burn slowly for trillions of years, to massive blue giants that exhaust their fuel in just a few million years. Their life cycles drive the chemical evolution of the universe, creating the heavier elements necessary for planets and life. Without stars, there would be no worlds, no biology, and no observers to marvel at the cosmos. If early massive galaxies formed far sooner than models predict, the very notion of the Big Bang may require reconsideration. Standard cosmology assumes that the universe emerged from a singularity approximately 13.8 billion years ago, expanding uniformly. However, JWST's observations of JS/GSZ 14 and other galaxies challenge this timeline. Some of these galaxies appear almost mature in their structure, as if the universe had already passed through formative epochs that, according to theory, should not exist yet. This raises profound questions. Was the universe truly finite at its beginning, or has it always been infinite? Could matter have appeared everywhere simultaneously, creating galaxies beyond our observable universe? Do these early galaxies hint at processes beyond the Big Bang, possibly connected to previous universes or alternate dimensions? Another dimension to this puzzle involves dark energy, the mysterious force accelerating the universe's expansion. Previously assumed constant, dark energy may evolve over time, influencing galaxy formation rates in ways not accounted for by standard models. If dark energy was weaker or stronger in the earliest epochs, it could explain rapid coalescence of matter into massive galaxies, unexpectedly high star formation efficiencies, structural organization in galaxies far earlier than predicted. Such observations suggest that our understanding of cosmic acceleration is incomplete, with profound implications for the fate and origin of the universe. JWST essentially allows us to observe the early universe as a natural laboratory for extreme physics. The conditions in these first few 100 million years push matter, radiation, and gravity to their limits. The early massive galaxies, high star formation rates, and unusual structures challenge our understanding of cosmological timelines. How quickly did structures emerge? Matter distribution. Was there enough ordinary matter to build these galaxies? Physics of star formation. Could exotic processes accelerate stellar birth? If conventional models cannot explain these findings, scientists may need entirely new frameworks, perhaps involving non-standard physics, cyclic cosmology, or even multiverse interactions. The implications are staggering. JWST has opened a window into a universe that is far more massive, galaxies assembling unusually fast. Highly organized, structures formed in the first few 100 million years. Potentially influenced by unknown physics, dark energy, multiverse, or cyclic processes. Scientists are now faced with the possibility that our cosmic origin story is incomplete. Every new observation forces a reassessment. Could there have been previous universes, or dimensions affecting early formation? Are we glimpsing a universe far older or far stranger than imagined? This is only the beginning. As JWST continues its mission, deeper and longer exposures will reveal even more about the early universe. Upcoming studies will focus on confirming the nature of the 87 early galaxy candidates, mapping star formation histories and chemical compositions, testing alternative cosmologies and theoretical models. The universe may be telling us something profound. The first few 100 million years after the Big Bang hold secrets that could rewrite the textbooks of cosmology. The James Webb Space Telescope has fundamentally changed our perspective on the early universe. In just a few years of operation, JWST has revealed galaxies that are far more massive, luminous, and structured than standard cosmology predicts. From JS/GSZ 14 to the 87 candidate early galaxies, these objects appear within 200 to 400 million years after the Big Bang, challenging the timelines established by lambda-CDM models. Key takeaways from these discoveries include rapid galaxy formation. Galaxies with stellar masses comparable to modern systems formed much earlier than expected. High star formation efficiency. Some galaxies appear to convert nearly 100% of their gas into stars, defying conventional astrophysics. Early structural organization. Spiral or elliptical features are present when theory predicts only chaotic, irregular systems. Potential new physics. Observations hint at evolving dark energy, cyclic universes, or interactions with parallel/mirror dimensions. These discoveries have sparked intense debate among cosmologists. Some argue that these galaxies are rare anomalies, while others contend that they may indicate a fundamental flaw in our understanding. Several open questions remain. How did such massive galaxies form so quickly? Were standard physics processes sufficient, or is exotic physics required? Could some of these early galaxies be non-galactic structures entirely unknown to science? Nobel laureates and leading researchers are exploring radical ideas, including conformal cyclic cosmology. Our universe is one cycle in an infinite chain. Parallel or mirror universes. Energy or matter may have influenced early galaxy formation. Variable dark energy. The rate of cosmic expansion may have fluctuated, altering early structure formation. If JWST's observations continue to hold, the implications are profound. Rewriting the cosmic timeline, the first few 100 million years may have been far more eventful than expected. Revising galaxy formation models. Traditional hierarchical growth models may be insufficient. Challenging the Big Bang. Early galaxy maturity and mass might require modifications to the initial singularity concept or its interpretation. Dark energy and dark matter. Observations may indicate variable dark energy or non-standard dark matter interactions, altering our understanding of cosmic expansion. In essence, the universe at redshifts Z May 12 looked dramatically different than previously assumed, suggesting a richer, more complex cosmic history. The power of JWST lies in its ability to see deeper into the universe than ever before. Each observation is a direct glimpse into the distant past, allowing astronomers to trace the formation of the first galaxies, measure star formation rates in extreme environments, detect unexpected structures that challenge theoretical models. Long exposure deep field images, sometimes taking 120 hours or more, reveal details invisible to previous telescopes. These observations act as natural experiments, showing us conditions impossible to reproduce on Earth. The next decade promises even more revolutionary discoveries. JWST and future observatories, such as Roman Space Telescope and extremely large telescopes, will help answer key questions. Confirming early galaxy candidates. Spectroscopy will validate which of the 87 candidates are genuine. Mapping chemical abundances, understanding how elements formed in early stars. Testing exotic cosmology models, CCC, parallel universes, and dark energy evolution will be scrutinized. Exploring the observable universe's limits, finding how far back structured galaxies truly exist. These investigations will either reaffirm current models with refinements or force a paradigm shift in our understanding of the cosmos. Beyond theoretical debates, these discoveries reshape humanity's perception of the universe. They challenge our sense of time, scale, and cosmic history. The universe may have begun differently than we imagined. It may contain structures far older or more complex than anticipated. The processes that shaped galaxies, stars, and planets could be far stranger than we can currently model. JWST allows us to ask questions once considered science fiction. Could previous universes have left imprints we can observe? Are there regions where physical laws differ? Is our understanding of cosmic history fundamentally incomplete? Science thrives on curiosity and engagement. The discoveries of JWST are not just academic, they inspire wonder and questions for the general public. Video creators, educators, and science communicators can explain the timeline of galaxy formation using deep field visuals, illustrate cosmic expansion and the observable universe, discuss speculative theories in an accessible way, from cyclic cosmology to parallel universes, Engaging the public ensures support for future missions and fosters a new generation of astronomers and cosmologists. JWST has opened a new chapter in cosmology. From massive early galaxies to the possibility of parallel universes, the universe is far stranger and more complex than previously imagined. While many questions remain, one thing is certain: our understanding of the cosmos is evolving rapidly. Each new discovery challenges scientists to reconsider what we know, and what we thought impossible is now within observational reach. The first few 100 million years after the Big Bang may have been a period of extraordinary complexity, full of surprises that push the boundaries of physics, cosmology, and imagination. As we continue to explore, one truth remains: the universe is not just a collection of stars and galaxies, it is a story, unfolding across billions of years. And we are just beginning to read its earliest chapters.